everyone, I'm delighted to be here to tell you about our work on program synthesis from partial traces. This work is done in collaboration with my colleagues Victor, Joey, and Daniel at Amazon, and it started while I was a summer intern there. If you've ever used cloud computing for anything, chances are that you've seen a console like this one, where you have some computing instances identified by some IDs, and they show some form of status. And you can use this to perform actions on your instances, such as click a button that says stop instance to stop them from working. What you might not have seen is that under the hood, your cloud computing console may be keeping track of your actions. So when you click buttons in the visual interface, it creates events showing the actions that you took. So let's please consider the following task, where you select some instance in your cloud computing console, and you click a button that says stop instance to stop it. Then after some time, you'll refresh the status of your instance to check if it's already stopped. If it is, you're done, you go home, you're done for the day. But if it's not, you'll go and press a button that now says force stop instance, just to make sure that it's really stopped. Each of these actions will produce an API call that gets recorded by the console. So in this case, when you press stop instance, you will record the very aptly named API stop instances along with its inputs and outputs. Then when you refresh the status, you create a call to describe instance status. And the last call calls again stop instances, now with a parameter force set to true. We can interpret these sequence of API calls as a description, as a trace that represents the task that you were doing. And as you execute this task more times, you get different traces showing the differences in different executions of this task. So as I said, we don't always make that call to force stop instances, so we won't always have the second call to the stop instances API call. If you execute this task very often, maybe every day, maybe even more, after some time you'll have a lot of these traces showing this task that you execute a lot. These traces are already being used by monitoring or billing, so we propose to give them a new purpose. Our goal is to synthesize programs that execute the task represented by these traces. And our end goal is to offer this program to the users to allow them to have a one-click automation of a task that they perform often. The main challenge in this is that these traces of APIs are very incomplete. Although the APIs that are made in the task get recorded, we don't really just want a program that will reproduce these traces. We want to be able to see additional data and control flow to actually produce the user intent and to have a program that will indeed perform the desired task. And even if our traces are very in-depth, there's some computation that only happens in the user's head. So when I said that we'll check the instance status, that is never going to get logged because it's really only happening in the user's head. So today I'm presenting a synthesis framework that we developed for this goal called Siren. Siren takes partial execution traces as the input specification, and by recovering hidden computation, it creates a program that will generalize beyond these traces and actually automate the task the user has performed. And at any time in synthesis, Siren holds a candidate program that is correct. It satisfies our correctness constraint, which is as follows. We consider a program P to be correct with respect to our input traces if for every trace there is an input sigma such that P executed over this sigma will produce that very same trace. Siren starts with an initial program that very intuitively, I hope, satisfies that correctness constraint. So we take the traces and we plug them directly into a cascading if-then-else statement where each branch is just reproducing one of these traces. Then we introduce a variable called branch that works as a dispatcher variable, and it is just describing or selecting which branch gets executed. So recalling our correctness constraint that the program is able to reproduce all traces, hopefully it's pretty intuitive to you that this program satisfies that constraint. If you set branch to 0, you reproduce the first trace, branch to 1, second trace, and so on. Even though that is correct, I hope it's also clear that this is not enough. It doesn't really produce any traces beyond what we've seen, and it for sure does not satisfy the task that I described to you in the beginning. So let's look a little bit under the hood at how Siren will improve this program. So after the initial program, we will go through a series of program rewrites that will improve the program. And some of these will make calls to an example-based synthesizer to uncover hidden functions. The initial program, as I showed, is correct by construction, but it has no uncovered hidden computations, such as the one that happens in the user's head, and it doesn't generalize beyond the traces, so it doesn't really perform the task that we're looking to perform. So the main goal of the rewriting will be to be able to generalize beyond what we've seen in the traces. And this rewriting is basically a search over a library of program optimizing rewrites that we have defined in Siren. Each of these rewrites will maintain the correctness constraint, so the program remains correct, and it will improve the program by lowering a predefined cost metric. Our cost metrics penalize syntactic complexity and incentivize reuse across traces. But if the user would like to improve the program for some other metrics, Siren's method is agnostic to the cost. So some of these rewrites are very compiler-like rewrites that don't really change the semantics of the program, such as noticing that some value gets used a lot of times and hoisting it into a variable that is defined above, or noticing that some of these API calls are showing up in every single branch, so we can again hoist it out of the if-then-else branching structure so that they're in the main body of the program. All of these lower syntactic complexity of the program, thus lowering also our cost metric. More interesting are the rewrites that try to uncover hidden user, well, hidden for us, but user intent. One of these is Siren is able to realize that this whole branching structure that we have here is just defining the value of C1, which is a simple constant. So it makes sense to make C1 instead of a value defined in the program, something that the program takes as input. So we rewrite it as a input parameter. This will lower syntactic complexity as before, and it removes dependency on our branch variable. That doesn't really have a semantic meaning, so this is also something that will lower our cost metric. By doing that, we create a more general program that is now able to perform more actions. Another rewrite will look at the second usage of branch, which is deciding whether or not we make that second call to stop in instances. And the goal here, the question that Siren is asking, is can we infer the user's intention from what we can see? And here we can see a lot more than before, because we have the previous two API calls that now we have access to the data they give as output. So the way Siren finds that out is by replacing this use of the variable branch with a now undefined function f that takes as input all the parameters available in the program for now. So the output of the two API calls, as well as I1, which we take as a parameter. This will once again lower the syntactic complexity of our program and remove the dependencies on branch and make our program more general. Of course, we still have a problem. This is not a complete program. F remains undefined. So we have these rewrites that allow us to generalize and maintain correctness of our program, but we still have these hidden functions that we need to uncover how they work. And that's where the example-based synthesizer comes in. So we have this function that takes as input everything defined in the program up until now, and then its output is used after its call. The main insight that allows us to find out what to do with this function is that for every trace, we have access to the value of each of the inputs of these functions, as well as the output. We see the output to stop instances and describe instance status, which is the inputs to the function, and we can see whether or not we made that second call to stop instances, which is the output of this function. So we can go for every trace and collect the input and output pairs for this now undefined function. And this is exactly what example-based synthesizers take as an input. So we use an off-the-shelf example-based synthesizer to get an implementation for our function, which it can then plug back into our program, having now a complete program. In this case, the implementation will select the third input to F, which is the output to the describe instance status call. And it will compare that output with the string stopped, which is exactly what I told you we were doing in our task. So this is Siren's complete synthesis procedure. We have an initial program that is correct by construction, and we apply a series of rewrites that generalize beyond the traces while maintain correctness. Some of these rewrites also make calls to an example-based synthesizer, which allows us to uncover hidden computation. We initially developed Siren for traces of API calls, but we noticed that we aren't really limited to that. We can work with any trace that is a sequence of function calls along with their inputs and their outputs. And one example is system traces, which your operating system might keep if you're doing for example, some file system manipulation. To show this variety, we evaluate Siren on 54 benchmarks, including cloud automation, file system manipulation, and document editing tasks. We collect these from AWS Cloud Automation scripts, as well as the Blink automation library, and some related work on API discovery. We ran all benchmarks with a 5-minute timeout, and what I'm showing here is a cactus plot, where for each timestamp in the x-axis, it will tell you on the y-axis how many instances were solved under that time. And the running example that I showed you, the stop instances task, takes just under 1 minute to synthesize. Within the 5-minute timeout, we were able to synthesize 72% of our benchmarks. And these will include programs with up to 4 control flow structures, such as conditionals and loops, and up to 2 hidden functions synthesized using the example-based synthesizer. Importantly, all of the benchmarks that Siren synthesizes are correct. We know that this program will be able to generate our traces. For comparison, we tried to run an LLM on the same kind of specification, and we found that it would output the correct program in only 53% of the benchmarks. So I showed you how Siren enriches compiler-like optimizing rewrites with calls to an off-the-shelf example-based synthesizer, which allows it to control data and control flow and synthesize hidden functions, thus producing general-purpose scripts from partial traces of their execution. And I wanted to ask if you can think of other applications, if you work on something that produces these kinds of partial traces with sequences of functions and inputs and outputs, but with some computation missing in the middle. If you do, please let me know either here or at my email. Thank you for listening. I'll take any questions.
Thank you for the interesting talk. I think it's really practical and helpful idea. But if we apply this to a real-world application, how can we determine if the partial traces share the same intent?
Mm-hmm. That is a great question. In our case, we selected the traces performing the same task. It's not something that we work on Siren, but there is some related work that uses techniques like clustering to select traces that are performing the same task. But as I said, it's not something we've looked into.
But is the approach robust to some, some outliers which are the partial traces that don't share the same intent?
Not right now, although that is a extension that I am hoping to work on in the very near future.
Okay, thank you.
Thank you.
Thank you for presentation. And I want to ask that what is the average length of your trace and will it influence your performance, synthesis performance?
Length in number of function calls?
Yes.
It's a good question. Do you have an idea? Maybe 10, 15-ish calls, function calls? Around 10. Right, when we introduce loops, these loops will show up unrolled in the traces, so you have the same API call happening a lot of times.
So if you have a longer trace, will you spend more time to synthesize a program?
A longer trace, yes, yeah. Yes, because in general it means that the program has to be more complex, and the more number of calls that we need to make to the example-based synthesizer, the longer it takes to synthesize.
Okay, thank you.
Thank you.
Hi, Milin Chibi from Uber. Interesting work. Are you assuming that these are sequential programs? How do you deal with anything in traces that's because of non-determinism?
Yes, for now we are assuming they are sequential, and we are not robust to calls happening at the same time or independent calls that may happen in different orders. If that does happen, what might happen is that you have the conditional structure, where in one branch it happens in one order, in the other it happens in the other order. But that is another extension that I hope to be working on in the near future. Thank you.
Thanks for the great talk. A cool application that I can think of right now is maybe trying to try to synthesize an integration test for GUI apps from interacting with the application. So that might be a cool application. Okay.
When you do that, does it create these kinds of traces?
Yeah, I mean if you write an iOS app or like web apps, it's very likely that they have some logging facilities. So we can use those logging facilities to like create a general integration test from several traces. So that may be cool.
That sounds very cool. Can you tell me your name so I can find you later?
Okay, I'm Jay Lee. It's just a random thought, so.
Thank you.
Cool.
Thank you. Thank you so much.
Great.
Maybe your last question?
Thank you for the great presentation. And I just noticed that I need this tool because I was a TA of a really big class. It has a 150 students, and I had to set up the VMs for each student, and I spent 3 nights to set all the things up. And my question is that the tool is generalizable to the Python scripts that I use, so I can. It's like there is a scripts that download some packages and install some softwares, and I need to check that it's actually installed and it can be discovered in environment variables. So I need those custom operator that is written in my Python script, and I need this synthesizer to do the job I'm supposed to do.
Okay. What would be the logs in this situation? So while you're executing, for, I guess, for one student out of the 150, you are doing this for a VM, right? And do you know what kind of logging that VM is doing?
Like the one typical example is that I have to call the apt-get install. So it's going to it's going to leave some logs in it.
Yeah, that seems like it should work because you have the inputs and the outputs. So in these scripts, from what I understand, they're just basic sequential steps, right?
Basic sequential steps and some checks that if the apt-get fails, do other things.
Sounds like,
Perfect.
Sounds like perfect application. Yeah.
Okay, thank you.
Thank you.